Hello, welcome to this talk. My name is Behzad and I will be happy to present this paper entitled An Experimental Study of Reduced Voltage Operations in Modern FPGAs for Neural Network Acceleration. To begin, I will give a brief overview. Our main motivation is that the power consumption of neural network is a main concern. To alleviate this issue, hardware acceleration is a very common technique, and among the hardware accelerators, FPGAs are getting more popular because they are providing better flexibility than ASICs and better throughput than GPUs. However, the problem is that their power efficiency compared to the ASICs is a problem. It is reported to be at least 10 times less. In this work, our main goal is to bridge the power efficiency gap between ASIC and FPGA-based neural networks using undervolting below the nominal level. Our experimental setup is based on 5 image classification workloads, 3 Xilinx UltraScale Plus platforms, and also 2 on-chip voltage rails. And among the main results, we observed that there is a very large voltage guard band below the nominal level for real FPGAs, 33% of the nominal level. By eliminating this guard band and also further undervolting, we achieve more than 3 times power efficiency gain. Here is the outline of the talk. I will first briefly discuss the motivation behind the work and provide the necessary background. First motivation. The main motivation behind the work is to improving the power efficiency gain for FPGA-based neural networks. Although they are getting much popular, but their energy efficiency compared to the ASICs is an issue. On the other side, it has been shown for CPUs, GPUs, and DRAMs that undervolting can be an effective technique, especially by eliminating the large voltage guard bands. In this work, we are aiming to understand the effect of the potential of undervolting FPGAs for a power efficiency of neural networks. And I will briefly provide background about neural networks, that they are getting much popular, and also they have inherent resilience to the errors. FPGAs, they can provide better throughput than GPUs and better flexibility than ASICs. And finally, undervolting, which can provide power efficiency. On the other side, and as an overhead, it can have reliability or performance issues. Let me elaborate on our main goals of this work. Our primary goal is to bridge the power efficiency gap between ASICs and FPGA-based neural networks using undervolting the supply voltage below the nominal level. And as a secondary goal, we study the voltage behavior of real FPGAs such as guard bands. We study the power efficiency gain of undervolting for neural networks. We study the reliability overhead of this technique. We study the frequency underscaling to prevent accuracy loss. And finally, we study the effect of environmental temperature. I will briefly explain the experimental methodology now. The overall methodology of our work has been shown here. Our work is based on convolutional neural networks in the classification phase. It means that our input is the pre-trained model of the neural networks. We choose 5 image classification workloads that are listed here. They have different sizes from few kilobytes to hundreds of megabytes. For mapping neural network models into the FPGA, we use an industrial tool called Xilinx DNN. And for the hardware platform, we choose 3 identical samples of Xilinx ZCU102. It is based on hardware-software designs, and in this design, hardcore ARM processor is used for data orchestration. Also, FPGA part is used for convolutional neural network acceleration, which we are aiming to undervolt. And for the undervolting, we are working on 2 voltage rails, on-chip voltage rails, which are accessible through PM bus. VCC int and VCC BRAM. VCC int is used by share for DSPs, lookup tables, and buffers, and the VCC BRAM is also dedicated for clock ramps, and the nominal voltage for both of them is 850 millivolts. It is worth noting that our early analysis at the nominal voltage level showed that the vast majority of the power is dissipated into the VCC int, and then it is negligible power consumption in the VCC BRAM. So because of this observation, the rest analysis is based on VCC int. Now I will discuss the experimental results. And first I will start with the overall voltage behavior. The overall voltage behavior for benchmarks and platform has been shown here in this figure. As you can see, there is a very big voltage guard band below the nominal level. The size of this guard band, we observe it is 33% with a slight variation. There is no performance or reliability loss in this area, and there is a power saving. We think that this is added by vendor to ensure the worst case conditions. Below this guard band level, there is another area which still we have power saving, however this time with the cost of accuracy loss. We call this area critical region, and it is much narrower than the guard band. And finally, by Further undervolting, we observe that the system crashes and there is no output in the output of the FPGA. As mentioned, we observed a very slight variation across platforms and benchmarks. Now I will explain how power and reliability are affected when we are undervolting into those three voltage regions. First, power efficiency. We achieve more than 3 times power saving by eliminating the voltage guard band and also by further undervolting below the nominal level. Most of it is achieved by eliminating the voltage guard band through 2.6x, and the rest is by further undervolting. There is a slight variation across 3 platforms and 5 workloads. And in terms of the reliability, as you can see, we observe no accuracy loss in the guard band. However, there is a very big accuracy collapse observed for all the benchmarks in the critical voltage region. Also, as you can see, there is a slight variation across 3 platforms and 5 workloads in terms of the VA crash and VA mean. Now I will explain the frequency underscaling technique. In this technique, our aim is to simultaneously reduce the frequency with supply voltage to prevent the accuracy loss in the critical voltage region. And our aim is to find the maximum operating frequency for each voltage level below the VME, which there is no accuracy loss. It is clear that this may lead to performance and energy efficiency loss since we are reducing the frequency. Where our result has been shown in detail in this figure. As it can be seen, the first 2 columns are the voltage levels below Vmin and associated FMX setting, and the rest 4 columns represent the performance, power efficiency, and energy efficiency parameters. The best setting for each parameter is highlighted here. We found that Vmin with the default frequency is the best setting to achieve high performance and energy efficiency, since by underscaling the frequency, the performance and energy efficiency reduces gradually up to 30 and 25% respectively. However, due to the reduced frequency, the power efficiency improves up to 25%. There is also 44% of power consumption reduction at VA crash due to the voltage and frequency underscaled simultaneously. I will now discuss the effect of environmental temperature. Temperature has main impact into the power consumption, specifically the static power and also the reliability. In our experiment to generate the temperature range, we use the speed of the fan. And also to monitor the temperature, we use the PM bus interface. About the effect of temperature into the power consumption of our accelerator, we observed that it has a direct relation between temperature and power consumption. However, the impact of the temperature into reduced voltage level is much less into the power consumption. On the other side, about the reliability, we observed an indirect relation between the temperature and also the accuracy loss. Also, finally, the important point is that the temperature does not show a very meaningful impact into the size of the guard band and critical areas. I will now discuss the related works. First, undervolting. This technique has been studied for CPUs, GPUs, ASICs, and DRAMs, and in most of these devices, they have observed a very large voltage guard band. In this work, we are also expanding those studies for FPGAs, real FPGAs, and also we confirm large voltage guard band. About the power efficiency for neural network, there are many works related in the architecture, hardware, and software levels. Also, undervolting has been studied for, especially for ASIC-based neural network accelerators. In our work, we extend those hardware-level techniques, undervolting techniques, for power saving in FPGAs. And finally, about the reliability in neural network, there are works in analytical and also simulation-based studies. And also on real hardware, they have been studied, especially on DRAMs. In our work, we studied the reliability of the neural networks mapped into the FPGAs when they are working in reduced voltage levels. Now let me conclude by giving a summary. In summary, we achieved more than 3 times power efficiency gain for FPGA-based neural networks through undervolting. 2.6 of this is coming by eliminating the guard band without any cost. However, the rest 43% is coming by further undervolting below the guard band, and it has the cost of either accuracy loss when the frequency is not underscaled or performance loss when the frequency is underscaled. We conclude that undervolting is an effective way to achieve significant power saving for FPGA-based neural network accelerators. And as the future work, we are working to expand our technique for FPGA clusters and also for other neural network models and tools. Thank you for your attention, and please feel free to contact us if you have any comment or question on our work. Thank you.